So what's that? What type of code? BCS?
The BCS.
Yeah, we
1D. Don't worry about full deferral, just simple superfluid.
okay. We already have that code.
Okay, so I want a very simple 1D version of the code that we can put on Google Drive that will run in Collaboratory.
Mm-hmm.
And then what I want to do with it is I want to try and implement our cooling algorithm.
Cooling.
Yeah, quantum friction.
So what's that?
So let me just show you briefly. Go here, I'll send you to the link. Okay. I'll send you an email because it's going to get lost.
Okay.
Whoops. Email. Shunda.
Huang.
Okay, here you go. See if you can open that.
So when you say, okay.
Okay, do you see this?
Yeah.
Okay, so this is the basic idea. I think I've talked to you about this before, but maybe not. Hang on, someone's calling. It's Ted. I'll call him back in a second. Okay. So you know about imaginary time cooling, right?
Yeah.
So if you implement the Hamiltonian and you change the time to imaginary, it cools.
And you get the ground state.
Okay, here is a derivation of this in a particular way. Okay? So what you want to do is you want to go downhill. Right? You understand this is steepest descent?
Oh, yeah.
Okay. So, and a continuous version of that is, of course, to just d psi dt is equal to the descent direction, which is like this, which is equivalent to regular evolution with the Hamiltonian if your phase is I, so imaginary time. Okay? Okay, that's what we do quite frequently. Now, that, of course, is not unitary, so you'll lose particle number. The normalization will change, right?
Okay.
And so if you want to not change the normalization, then you have to subtract a chemical potential as well, which you have to choose to be exactly this value.
Okay.
And that essentially makes the change orthogonal to the original state.
Orthogonal.
Oops.
Okay.
Sorry, I don't want to do that. Right? So the change vector is h plus mu. Oops, sorry, that should be a minus. The change vector is h minus mu.
Okay.
And the d psi should be orthogonal to psi.
Okay.
And if you evolve with d psi being orthogonal to psi, then it just rotates. It never changes the length, right? Make sense?
Because they're always perpendicular, right?
Yeah. The change is always perpendicular, okay. So it just rotates, and if it's continuous.
Okay.
Okay, so that's all that does. Now, you can rederive this in a slightly different way. So here's the idea. We want to implement evolution with some new Hamiltonian HC, which we'll call the cooling Hamiltonian. Okay? And what we want the energy to reduce.
Okay.
So we compute the energy. Now the energy is computed using the original Hamiltonian. Okay?
Okay.
So E dot is dE d psi dagger dot plus dE d psi dagger psi dot. It's just chain
Okay,
rule.
okay, yeah.
Okay. And then this guy here is H psi, and this guy here is psi H.
Yeah.
Right? And then psi dot is given by this equation here. And so you end up with this formula.
Okay.
Is that big enough? You've got this on your computer
Yeah,
as well.
I can read that, yeah.
Okay. So you end up with where did I put that formula? This formula here. Okay? So it's the expectation value of the commutator of the original Hamiltonian with the cooling Hamiltonian.
Okay.
So if you evolve with the original Hamiltonian, energy is conserved because they commute.
Wait. So you say energy here is conserved?
If you evolve with the original Hamiltonian,
Yeah.
right, then HC is H, it's 0.
Okay.
So okay. Now, so we want to choose HC so that this term is negative definite, right? So that E goes downhill.
Okay.
So we rewrite this term, and I include the normalization here, but we rewrite it in terms of the density operator, psi dagger.
Okay.
And then this expectation value can also be written as a trace.
Yeah.
And then you can rearrange the terms cyclically.
Let me see. Oh yeah, maybe, yeah.
The first term is RHHC, so that becomes HCR because the trace is cyclic, and the second term is the same thing except.
Yeah,
okay. And so now you can see that if you make the last part, if you make HC equal to the last part, daggered with a negative sign. Okay. Then this whole term looks like HC dagger HC, the trace of HC dagger HC.
Yeah.
And that's going to be, because that's the trace of a Hermitian matrix times itself, that's a perfect square, so that's always going to be positive, and if you put the I in here, then it's always negative, and so you can guarantee the energy is going to go downhill.
Okay.
Okay, so this is, in some sense, an optimal choice. Okay?
Okay.
So now if you do that and just look at what evolution with that HC corresponds to, it turns out that it's exactly evolution with the original Hamiltonian, minus a mu, the mu is built in there, and with an I. So it's imaginary time cooling.
Okay.
So this is another way of deriving the imaginary time cooling. Okay? Now the interesting thing is you don't have to choose HC to be the full Hamiltonian. Instead, you can choose it to be something local in position or local in momentum space.
Wait. So what you just say is the local in the momentum of space?
Or position, yeah.
So what you mean by local means? Just
So in local in position space means it's implemented with a potential, V of x. Local in momentum space means it's implemented with some modified kinetic energy, which would be some function of k.
Okay, people call that local.
Yeah, do you know what I mean?
I'm not quite sure because that's kind of
Okay, so a non-local potential
it's kind of like what.
would be something like this. Psi, so V
Or not depend on R.
psi,
Something.
right? Let's do it with wave functions. No, I'll do it with brackets. So this would be a non-local potential in general. It would be the integral
Why?
over x of some function v of y and x times psi of x. Right?
So you say this term is not local.
So this is a completely general operator.
Okay.
Right? This is just the operator in the position basis, and I'm integrating it. That's the matrix multiplication.
Okay.
Okay? A local operator would be one where, so that's non-local. A local potential would just be v of y psi of y. Oops.
So it's
Right?
not dependent on the position.
It does depend on position, but locally,
Okay. Only on that work.
right?
Mm.
So it means that v
So only
of
in a
y
finite range, right?
is delta x minus y v of y, right?
Okay.
So it's a delta. It's got a delta function.
Okay.
So in a matrix form, it's a diagonal matrix.
Okay.
In the position basis, of course, in the momentum basis, it won't be.
Yeah.
Okay. In the momentum basis, something that's diagonal would appear like a convolution, right? So this would be diagonal in momentum space. You can use the convolution theorem, so it's just multiplied by. Make sense?
Yeah.
Okay, so Kc is something like this, diagonal in momentum space. And V is something like this, diagonal in position space.
Okay.
Which means when we implement this with, say, the split operator method, all we have to do is just multiply,
Okay.
right? Nothing tricky. All right. Now, you can go through the same procedure, and if you make Kc local or Vc local, you find that the terms factor out, and what you find is that your potential, or your kinetic potential, is just, it's basically the same thing as up above. It's this commutator of RH. But you evaluate it in position space or in momentum space. You just take the diagonal of the matrix. Okay?
Okay.
It turns out, if you do this, this is just the time derivative of the density. Okay?
So it's not obvious how the density come to play here.
Okay, it comes from this. So the density is just the diagonal of the density operator.
Okay.
Oops.
Oh.
Yeah. You see? You can see my mouse? I don't have to highlight?
Oh, I can see that. Okay. So
Yeah, okay. So it's just the diagonal of the density operator, and then you have to look at the time dependence of the density operator.
yeah.
And the time dependence of an operator is just the commutator of the
yeah.
operator with the Hamiltonian, right?
Yeah.
And so you just carry this through. If the dense, let's see, what did I do here? Oh, since this is in position space, the potential terms commute.
Yeah.
I mean, they don't commute, but the position space part is 0.
Yeah.
And so this is equivalent to the kinetic energy part. What happened to my sign? Ooh, there's a sign error somewhere.
You just switch maybe you remove the minus sign in front of the last term.
Yeah, one of them needs a minus sign removed. Okay, well, one of the things when you implement this, you'll have to check very carefully about the signs. Anyway, right, so now you see it's just this guy here, and this is exactly what we wanted.
Yeah.
Okay. So that's how you get these, up to the minus sign. Now, this should make a lot of sense. What do we do? If the density is increasing at some point, then what we want to do is we want to turn on a potential at that point. And that will try and push the material away from that point, right?
So you increase. So when density increase at some point, and then you increase potential at that point.
Yeah. So basically, if the system is such that there's a current causing the density to increase, the currents are flowing together, you put a potential finger there that pushes them away.
Okay. Yeah.
So you're trying to basically stop all the currents by manipulating the external potential.
Okay.
Make sense?
Yeah.
Okay. And the same thing happens in kinetic land, but I don't know how to think about that. It's the kinetic, the momentum current. Sorry, the Fourier transform of the current, basically. It's a weird thing.
Yeah, that's kind of...
And it's a potential in Fourier space, so it's hard to think about, but it works.
It's not intuition. Okay.
The formulas are just implemented by this.
Ah.
If you do it in the basis, you basically act with the Hamiltonian on the state.
So what's the...
And then you take the result in either position space or in momentum space. And you take the imaginary part of that.
So what that symbol means?
Imaginary part.
Oh. Okay. So.
Okay?
Mm-hmm.
So it's really easy to implement.
Okay.
So here I've implemented it for the Gross-Podolsky equation. So it looks familiar. I've got my K, my X's. I've got these two coefficients here, my kinetic energy, etc. I'm doing split operators, so I'm applying EK, EV, EK, EV, etc., etc. In each of these, I compute either KC or VC,
Okay.
and I add it to the original Hamiltonian.
Mm-hmm.
Okay.
Mm-hmm.
Oh, that's an interesting question. Oh, I should do something here. Oh, that's interesting. Okay, hang on. I want to add one more parameter to this. I want to have beta naught equals 1. Okay, so I'm evolving here with some portion of the original Hamiltonian, some portion of the cooling, the
cooling Hamiltonian.
Position cooling potential, and then I have some portion of the momentum. Okay. 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 So now I just evolve these. So I want to do here, I also want to go self.beta naught. Okay. So how do I compute the cooling potentials? I take so for VC, I take psi, I Fourier transform it, I multiply it by the kinetic energy, I inverse Fourier transform it. So this is this guy here. K acting on psi in position space. Which is, I could also do this, because the real space will cancel out. But anyway, I've done it with the K's here, because it's a little faster. Okay? Then I just multiply by psi conjugate, take the imaginary part, multiply by 2, and I've chosen a particular normalization here.
Okay.
Okay? And then I multiply it by beta v. The kinetic energy, I do a similar thing. I Fourier transform to get psi of k. I act with the self-consistent potential, Gn times psi. Right? So that's V acting on psi, because there's no external potential here. Okay?
Okay, so the Gm times psi is the interaction terms in GP equation, right?
This is the potential, the internal potential.
Okay. Internal.
Okay?
Okay.
Yeah, there's no external potential here.
Okay.
So the potential it's the mean field potential.
Okay.
And then I Fourier transform this. So now this is in momentum space. And then I do psi k conjugate times v psi k in momentum space. Take the imaginary part, normalize it.
Okay.
3 times that. So that's this formula. Okay?
Okay.
So you see it's in momentum space. Got it?
Yeah.
That's it. The energy is just the regular energy. That's
so
all right. So now if I implement this, then this is what I find. It'll compute this in a second. But as you evolve, this is the energy as a function of the cooling with kinetic, with potential, and with both.
Oh.
Now, what I wanted to do here, I wanted to try what happens if I do beta 0 is 0. This is what it didn't do. This also has regular evolution. Interesting. Yeah, okay, fine, so that makes sense. So you have to have some evolution if you want the cooling to work. Right? If you just try and do so here's the thing. Okay, this is sort of further, but if you just try and cool with kinetic, it'll remove so let's say you just try and cool with the potential, it'll remove all of the currents from the system. Okay?
So when you say evolution, that means we need some parts of the original Hamiltonian, right?
Kind of. Yeah, so if you just try and remove so if you let's say we just do the cooling with the local potential, it will very quickly remove all the currents. Okay? Once those currents are gone, if you do not evolve with the regular Hamiltonian, the system will not rearrange itself. Right? So if you have a bulge in the middle, then what should happen is, let's do it this way, beta 0 equals 1. Okay, so this is oh, I don't know if this works. I don't think this works. Does this work? This doesn't work. Yeah, I can't show you here. Sorry. Do you know what I'm trying to say? So what I did in this case is I started with a bulge in the center.
So like external
And that
potential.
bulge should move out because of the mean field pressure. But if you don't have the real evolution, it never moves out. What happens? The currents just stop, and it just sits there. Okay?
Yeah, try to think that physically.
So you always need some original Hamiltonian, or you need to both do kinetic and potential, and then it works. Okay? All right. That is not what I need you to do. What I want you to do is I want you to implement this with... That's interesting. Let's see. I want you to implement this with the fermions.
So for fermion, I need the fermion GP-like equation, right?
No, do this with the SLDA, or the BDG.
Okay, also BCS code.
Yeah. So 1D BCS code. All right. For your case, I'm wondering if you want to do split operator or not.
So, okay. So here, what the split operator exactly means here?
So okay, so let's do this. Let's do this two ways.
Oh, I see.
Okay. So you need to implement this equation, right? Okay. What I would suggest you do now, you'll need to implement this for every single wave function.
So all the
right?
states.
So all your single particle states will have to evolve like this.
Yeah, because
Okay, so what you do is start with Hartree-Fock, okay? So don't put the pairing in to begin with.
Okay, so no delta.
Because then you don't have to worry about delta, you don't have to worry about the kinetic energy. Sorry, the regularization.
Okay.
Okay? The tricky part with the delta is that, of course, you need to have a whole bunch of states. Okay? So for now, just do it with, we do want to do delta. So you might want to put your code that has the delta. But for now, just start with Hartree-Fock. So you fill up n states with fermions. You make sure they're all orthogonal. So you should probably get these by diagonalizing a Hamiltonian.
Yeah.
Okay. Now you have to keep track of all of them. This is why we have to do it in 1D. And then what you do is you simply compute the Hamiltonian acting on these guys, right?
All the wave functions.
Now, yeah. Now the Hamiltonian has the sum over, right? It has a density in it. At least the nonlinear. If you do the BDG or something, it does. Actually, BDG doesn't. Well, okay. We can build this up. You can start with free fermions in some external potential. So your Hamiltonian is just the kinetic energy plus V.
V terms.
So maybe you put this in a harmonic oscillator. Okay? The next stage will be to put a Hartree term in. So there'll be some density dependence. Okay? But you use all your previous code to calculate the densities and the taus, et cetera, right? All right. So your Hamiltonian depends on the reduced quantity, like the sum over all the densities. Okay? And so all you do is you just evolve each of the single particle states according to the Hamiltonian. Right?
Yeah, okay.
And the Hamiltonian itself will depend on the full set of the psi n's.
Yes. Okay, so what we doing is, what we used to do is not depend on time. Now we do that with
Yeah.
Okay.
Now, so the question is, how do you implement this time step? Right? And there's a couple of easy ways to do this. So the easiest way is you just use some sort of evolver, and you could use my pi time ODV, or you could use one of the evolvers in SciPy. Right?
Okay.
Like there's ODE evolvers. And so all you need to do is you need to write a function compute dy dt that computes this guy.
Okay. Yeah.
Multiplied by h, and then it'll evolve it.
Okay. Yeah. I may read your code. Yeah. I saw that before.
Yeah. So first of all, just implement everything and a function compute dy dt. Okay.
Okay.
And then from there I can. The split operator is a simple way of doing this when you can factor the Hamiltonian into kinetic and potential
okay,
pieces.
Yeah, I remember that. Yeah.
Okay. And the way it works is that
to a tiny, to spread that in time in very small steps.
You know how this works?
Yeah.
So the solution here is that ket of psi of t plus dt is equal to, so for a constant Hamiltonian, this would be equal to I to the minus I, well, let's do it this way, h
pass.
divided by I h bar dt. Right? Something like this?
Yeah. And then
what did I do wrong? Oh, too many. And this is approximately equal to...
Yeah, so because they are not commutes, right? That V and...
Yeah, exactly.
Okay,
so this is approximately equal to e to the k of 2...
half k V and half k something.
And then a full V and then a half k.
Yeah, I remember that.
Okay. And then each of these pieces can be computed exactly. Right?
Yeah.
And that's what we're doing with the EXP stuff. Okay?
Okay.
So that's an easy way if you want to implement it yourself without using a differential equation solver, you do this.
Okay.
Now, there's one trick, and Gabrielle can tell you about this a little bit more, but the V depends on the size, generally. Right?
Okay, because internal potential...
Yeah, when you have this, when you have a so for the free particles, this will not have any issue. But when you do it for the Hartree-Fock or the Hartree-Fock-Bogoliubov, the V will depend on the size.
Okay.
Right? Because you've got the nonlinear dependence, right? The question is, where do you evaluate this v?
And
And the point is, you actually want to evaluate it halfway through the step.
halfway. So when I apply the first part of the operator there and update the side, and then.
So I have to think about this.
So this is.
I think what Gabriel did, I think he took the psi and he evaluated it for the full step.
Mm-hmm. So different.
With the potential as it was at the original point.
Okay. So.
Then I think he would go back halfway with a v that depended on the difference of the two, the final step plus the original step. Because you kind of want this, I mean, what you want to do for this to work with high efficiency is you want this to be like t plus dt over 2, okay? You want the potential to depend on the value of the wave function halfway between.
Yeah, that's okay.
Otherwise, you want the full accuracy.
So you mean
and so you have to do something tricky. You either have to evolve halfway first and then reevaluate the potential, or you have to evolve the full way and then go backwards and correct it, or you have to do something like that.
Okay, I see.
I don't remember exactly what you have to do.
Okay. So people just compare different way to evolve, right?
People. I don't know who people are.
I mean, so like Gabriel, they try different way, like the halfway.
Yeah. So Gabriel tried implementing in plagiaries and found that he has a strategy which you can just ask him that works.
So this is a kind of like converge a bit faster or more accurately.
Yeah. Yeah. And if you don't do the splitting of the k's on either side, you don't get the accuracy as well. Right?
Okay.
And you can drive all this, but yeah.
Okay. I see. So that.
Okay.
Okay. Mm-hmm.
So I need you to implement for the start with free fermions.
No delta and.
No delta, no Hartree term.
Okay.
And implement a 1D version of this.
Okay.
And then what we'll do is we'll try putting this cooling potential in, and we'll see how well that works.
Okay. I will try.
Okay.
Yeah.
And the second one is we'll add the Hartree term, in which case your V will then depend on this, so we'll have to do something with that.
Mm-hmm.
And then the final one is we'll put the Hartree Fock. The Vogel-Bach. We'll put the pairing in.
Okay.
Okay?
Mm-hmm.
But I want this to be able to run on CoCalc.
So to run on Coca on
Colab.
So there's no difference, right? We just upload when the Colab, you just need some package to.
I mean, so the problem is if you have Python code, you have to actually install that.
Yeah.
Right. So I'd like you to use Python code, but typically what you will do then is you will do. You have to make sure your code is available somewhere.
Oh.
Let me see. Did I do this here? No. Okay, I don't want you to do this here because this is my superfluid project. Let's make a place for you to do this. Fermion quantum turbulence. Do you have a directory here that you're working in?
No. I have the code. There's a name here for code here. 1, 2, 3, 4, 5, 6. Okay, yeah, you can make a new one. That's my old code.
Oh, here? Tinder quantum turbulence?
Yeah.
Do you want it in there?
I'm not sure, yeah. I can put anywhere.
Okay, so we'll have the local quantum friction.
Okay.
Let me create a new Colab notebook for you here. You've got the email with this.
Mm-hmm.
Let me just copy this formula over here for you. And somewhere at the top here, I think I have a big set of equations.
Oh, new
We'll
command.
just put all those in for you. Okay, so there. So you've got access to this notebook. Don't muck about with this notebook too much,
Okay.
because this is going to be part of my superfluid demonstration app.
Okay.
Okay, but I'll delete this now. You've got that in the other notebook. Delete this. Delete this. And now the question is, how do you get some code in here? There's a couple ways of doing it, and I have a little bit of a demonstration on the top. I need to figure out the best way.
Okay. Yeah.
One way to do it. Let me just give you some options. Sorry, I need to open this with Collaboratory. So one way to do it is to mount the Google Drive.
Yeah. We did that before. Need some like authentic link or something.
And so you would want to do code, yeah, for example. And I don't know where your project is. If you want to use the, I don't know if you want to use this.
This is not up to date. Yeah, we need.
Okay, so if you don't want to use that, then you don't have to. But you understand, right?
Yeah,
you can add your system path, the drive. When you execute this, it's going to ask you for permission to use that. Right, and then you have to go and you have to give it permission, right? So you click this link, you go over here, you log in with your right Google account, and it's going to say, yeah, and then you allow it.
Okay, yeah.
Right? And then you copy this code, you put it back over here, and you paste it.
Yeah.
I don't see the actual. What?
The image stack?
Oh shoot! Yeah, you're right. I didn't want it in the demo. I want it in the in this one, the fermions. Yeah. So you paste it there, and then you have access to it.
Yeah.
That's one way. The other way is that you could, if you put this particular code on a public repository, right? Then, and actually, I think this is what I recommend you do. Create a public Bitbucket repository with just this code. Free fermions we're not giving away to anyone. Then you could just go pip install hg plus https://bitbucket.org.
I didn't see your screen.
Yeah. Oh, sorry. Okay. And I think this one's better because then this one won't require people to do stuff. There. Okay. So I guess you would do this.
So Chrome first.
And then, yeah. Something like that, right?
Okay.
If you make your package pip installable, then you could also do what I had before.
Yeah.
But you have to put a setup file and everything in there.
Okay.
Right. Something like that.
Okay. So yeah, first I will.
Okay.
I see.
So do it either way, and then make something in here. And one thing that might be useful is to let me add it at the very beginning. Is to do. I have some tools on here. Here we go. Oops. And make sure you use this one. use this trick of the sys executable. Otherwise, it won't use the right version of Python. So this installs some of my tools.
Okay.
And there's a simple thing in here for doing animations in movies. Okay.
Okay.
If you go to project, you'll see it.
Let's command or install the necessary package like the MMF util something like that, or I should.
It doesn't install anything big like that.
Okay.
So if you want those, you're going to have to pip install those yourself.
Okay.
This one installs this thing that has movies.
Okay.
Right, so you can make a movie, you give it some functions that return some data, and then it'll make an animation.
Oh yeah. Okay.
It's because you can't use the regular animation thing on Colab yet.
Okay.
And I'm not sure why, but there's a reason. Okay?
Okay.
So please make a notebook here that we can actually run and play with some of this cooling potential.
Okay.
Start with free fermions. That's the easiest thing.
Okay.
And then ultimately the BDG would be nice.
Okay.
Make sense?
Yeah, I know. Yeah. So, okay, another. Okay. Yeah, that makes sense.
And this should fit in very well with what you're doing right now because you have to figure out all the right. It's just density functional theory.
Okay.
The only thing new over what you already know is this guy.
Yeah.
Doing the time independence.
Okay.
Okay. Oh, so we can't do Thomas. We don't know how to do Thomas Fermi completion yet with this. So you have to actually do this evolution with a cutoff.
Yeah, for BCS we always have a cutoff, right?
Well, you can actually use the TF completion to get rid of the cutoff.
Yeah, I see.
But you can't. I don't know how to do that with evolution yet. Okay.
Yeah. Okay. We will see.
Okay. Good. How long do you think this will take to do?
Okay. Another thing is I already translate the Aura's code to Python with the DVR things.
Okay.
And maybe someday, yeah, and it works. And someday maybe we need to work on make some comments on that. So because some part of his code and the theory I don't quite understand. I'm still reading his paper and.
Sure. I can just we can just go through that quickly.
Now?
I want you to get the cylindrical basis working as fast as possible.
Okay, so basically the same, right? We have the radial.
The numerics, the numbers are different, right? The averaging factors. Do you want to share? Is his code here somewhere?
It's on the quantum fermion theory, not here.
Why don't you update everything on Colab so we can take a look at it together?
Oh, okay. Yeah.
Okay.
Okay. I kind of like this. I cannot dislike Colab. It's kind of hard. Not like Coca. Coca is easier. It's not that. Okay.
Oh, so what do you mean? The reason I want to do this is because then anything we do, we can actually have conversations with Gabriel and Oral.
Yeah. Okay. Yeah. So they don't use the Coca, right?
No.
Okay.
Gabriel probably could. He's pretty savvy, but Oral probably won't.
Okay. Yeah.
What do you need to do that you can't do easily?
No. So I say I just need to understand the theory maybe more in deeper detail.
No. But why do you like Colab?
Oh, Colab, because every time you need to execute something and pip something and authorization and that's kind of like nonsense stuff.
Yeah, I kind of agree. But it allows them to actually use it. So.
Yeah, I see. Yeah. Okay. Eventually, we'll move everything here, maybe.
But I can look on Colab too, CoCalc too.
Oh, but fine. Not now. Yeah, but yeah, I can.
Okay, but when you're ready, give me. Now, I probably won't be available much tomorrow or the weekend.
Okay.
But I would like this to proceed quickly, so let me know when you have some time. We can just sit down and go through Oral's code. I think I can tell you exactly what to do there.
Okay, so you may be free next Monday or something.
Yeah, I've got Thomas's defense.
Oh, next Monday. Okay. Okay, yeah. I will ask again so to see if you get some time.
Okay. But yeah, if you could get this free fermion thing like working really quickly, that would be very helpful.
Okay, I will start working on that today.
Because I think it's pretty straightforward. And then, yeah, Oral and Gabrielle are thinking about this right now.
Yeah.
So
okay, yeah, I need to play with the old code a bit and
okay.
transplant that code.
Yeah, but for free fermions, it should be really easy to implement.
Yeah, I will get.
And then the BDG, of course, you have to put the cutoff and stuff, which makes it a little bit trickier.
So I need to just in 1D lattice, right?
Yeah, 1D lattice, periodic box. It's very simple.
Okay.
And maybe we put a
external potential, like.
Yeah, I'm wondering what the external potential. I mean, you could do a harmonic oscillator, then the density has to go 0, so your box has to be big enough. Probably the harmonic oscillator would be the best thing.
Okay, yeah.
Because we know the exact solution. You could also do a cosine potential.
Okay.
I don't know if we know the exact. Do we know the exact solution? I think those are Matthew functions. They're not quite so simple.
So for 1D, they always have analytical solutions for some.
Do you know the solution to the cosine?
I don't know, but
potential?
I can look up. Yeah.
I think they're called Matthew functions.
Okay.
But I don't think they're completely trivial.
Okay, so maybe Hamiltonian. No, harmonica thing. Oh yeah, this is something we talked about before, and it's kind of.
Yeah. See, so they're basically the solutions to the Schrodinger equation with a cosine potential.
Yeah.
So they exist.
But the function is kind of not.
Right, but they're not quite as they're not simple polynomials.
Yeah.
They're probably implemented in Python.
Okay. Yeah. Oh yeah, they have. Yeah, I guess. I checked that some other day. Yeah. There's some version of this package they have a lot of bug, and then people online try to fix that.
Oh, I see. Okay. Yeah. So anyway, you can do them in few functions, or you could do a harmonic oscillator.
Okay.
Pick whatever you want, whatever's easiest. Okay. Good.
Okay.
Thanks, Chanda.
Okay. Thank you.
Talk to you soon.
See you.